Here's example 3 of finding the discriminant of a quadratic equation. So we're going to calculate and interpret a discriminant again. So same directions as before, find the discriminant of the given equation and describe the equation solutions without actually finding those solutions. So the equation this time is 2/3 plus 2/3 p squared equals 4/3 p. So a little bit messier because we have fractions now. And again, just like always, we need to put this equation in standard form first. But before that, let's go ahead and get rid of those fractions. So multiply both sides of this equation by 3/2, and we're going to get 3/2 times the quantity 2/3 plus 2/3 p squared. And then on the right-hand side, we have 4/3 p times 3/2. So on the left side, we're going to distribute the 3/2 into these parentheses here, and we get 3/2 times 2/3 plus 3/2 times 2/3 p squared. And then on the right-hand side, 4/3 p times 3/2. Well, the 3's cancel, and we have 4 divided by 2 gives us that 2 here, and we still have the p here. So 4/3 p times 3/2 all becomes 2p. And what happens over here on the left? Well, 3/2 times 2/3 is 1, and then that happens again over here. We have 1 plus 1p squared, which is really just 1 plus p squared. So all in all, this simplifies to 1 plus p squared equals 2p. So we transformed our original, somewhat messy equation because of those fractions into 1 plus p squared equals 2p, and that's a lot better. And it's perfectly legal, valid, legitimate to do that. Nothing wrong with that at all. It is going to change the values of a, b, and c that we get when we do the standard form thing, and that's totally okay. It actually makes this a lot simpler for us. So now we put it in standard form, subtract 2p from both sides, and we get 1 plus p squared minus 2p equals 0. And again, standard form says quadratic term has to come first, and then followed by the linear term, followed by the constant term. Another way of saying that is we can rewrite this in descending orders of powers. So descending order of powers of p, here's the highest power of p, here's the next highest power of p, and then the smallest power of p. Technically, we can think of that as 1 times p to the 0. So here's p to the second, p to the first, p to the 0. So this is in descending order of powers of p. Anyway, when we do that, we get p squared minus 2p plus 1 equals 0. And now we can identify a is 1, that's 1 times p squared. B is negative 2, careful with the negative sign there, that is attached to the 2, so b is negative 2. And then c is positive 1. Now we can calculate the discriminant. It's d equals b squared minus 4ac, as always. So plug in our values for a, b, and c, and we have the quantity negative 2 squared minus 4 times 1 times 1. So negative 2, when we square that, we get positive 4, and then 4 times 1 is just 4. So we end up with 4 minus 4, which is just 0. So the discriminant is d equals 0, and because d equals 0, then our quadratic equation, 1 plus p squared equals 2p, and also the original one, really, with the fractions, has one repeated real solution, and that is to say, one real solution with multiplicity 2. So we talked about that multiplicity briefly in the earlier section there. So here's a little side note. We didn't have to clear the fractions to do this problem. It's just nice to get rid of them if we can, because it really will simplify the calculations a lot. So if we didn't do that in this problem, then we could still put the equation into standard form, and we would have ended up with a is 2/3, b is negative 4/3, c is 2/3, and we would still get d equals 0, which we should, because if d is 0 before you change both sides of the equation, then d better be 0 afterwards. But the calculation would have been a lot more difficult with the fractions. So if you have fractions that you can get rid of, go ahead and do it. It will probably make your calculations a lot easier later on.